Hi everyone watching this video. My name is Tang William with metric number 22501. Today, me and my group with the name LeBron James would like to present the assignment of the digital signal processing course with the title Audio Equalizer for Music. Now let's introduce our group members. Our group consists of 4 members, which is me, Chu Weixiang, Eugene Ng, and also Wei Jianhui. For the introduction of the assignment, so basically, this project explores the design and implementation of a digital music audio equalizer using MATLAB with a primary focus on analyzing audio signal to enhance sound quality through the modification of the specific frequency components. This project focuses on the development of a 3-band digital audio equalizer utilizing the FIR method filtering techniques to manipulate bass, mid-range, and treble frequencies. For the objective of the assignment, this assignment plan to unravel complex problems using knowledge-based research method, including the design and implementation of experiment analysis and interpretation of data to provide complete information and accurate decision, and to design implement a 3-band digital equalizer, which consists of bass, mid, and treble using MATLAB. And lastly, enhance sound quality and provide real-time control over audio frequency components. Now let's talk about the audio source and data acquisition of our project. So the first one is the selection of source material. We have picked the track with the title in trend, which taken from the Bensound website. It is a high fidelity MP3 or WAV format to ensure a wide dynamic range for filtering. And also we have picked to cut it into a 60-second representative segment so that it can isolate it for the analysis. And the second one, which is the technical specification, we have picked the sampling frequency around 44,000, which following the standard CD quality and also obey with the rule of Nyquist frequency rules. And the bit depth is 16-bit, which providing high resolution for amplitude measurement. And for the channel configuration, it is converted from stereo to mono to ensure the consistent peak detection across the signal. Now let's move into the part 1 of the project, which is analyze the music. Firstly, we have used MATLAB app to find the maximum amplitude and the timestamp location. And as you can see, the two picture provided is the time domain waveform and also the data of maximum amplitude and peak timestamp. As a result, the maximum amplitude is 0.9772 and also the peak timestamp is 10.49 seconds.
So this is the frequency time component. So as the graph showing is the frequency domain representation of the signal. So as you can see, the majority of the signal's energy is actually concentrated at the low frequency region, which is below 1000 Hertz. And the primary peak was actually identified at roughly 65 Hertz with a magnitude of roughly 0.02. Actually, to fulfill this requirement of analysis, the spectrogram was generated using the window size of 1024 and an FFT of 2048. So meaning to say MATLAB will take 1024 samples of audios and also zero padding to reach 2048 points before performing the FFT. So first of all, for the spectrogram graph is actually show a very consistent vertical energy burst across the time axis, and it actually also correspond to the rhythmic beats of the track. So as you can see, the high intensity yellow regions is actually at the bottom of the axis to confirm the presence of the low frequency energy. But regarding to the 3D waterfall plot, it actually provides a topological view of the energy peaks and where the high of the regions represent the magnitude. So with this, we actually identify the maximum energy frequency is actually 86 hertz at the time snap of roughly 3 seconds. So with this, is actually you can notice that base FIR filter will be the most stress component for the equalizer system, and it's actually need to be carefully managed to avoid digital clipping and also given a high concentration of energy at this very specific frequency. So the other method to analyze the music and song is also use the statistical energy analysis, and there's two key matrices, which is the root mean square RMS amplitude and also the crest factor. So the RMS value we actually calculated with an average power of 0.21 is actually represented a sustained loudness the human ear can actually hear rather than just a single spike. And then the crest factor with like the ratio of 4.65, we actually prove that the track is highly dynamic and also progressive, and this data is actually act as a safety check in because it's able to tell us how much we can boost the bass in phase the next part before the audio start to clipping or distorting. Yeah. Alright, so this is the MATLAB output that we get about the power spectrogram, also the time domain energy distortion plot. So actually to bridge the gap between the time and frequency observation, power spectrogram is actually needed. So the resulting spectrogram actually show that the high intensity, which is the yellow color region, is at the bottom of the frequency axis and is centered around 86.13 hertz. And this region actually represents the most energetic moments of song, such as transient recorded at 3.18 seconds are dominated by low frequency based component lah. And then this dual domain approach actually provides more justification for focusing our upcoming filter design on a base and also sub base region of the spectrum.
An audio equalizer is a digital signal processing tool that allows us to adjust different frequency components in an audio signal. Instead of changing the whole sound, we can boost or reduce the specific frequency range. In audio system, signals are commonly divided into bass, mid-range, and treble because each range affects how we pers- perceive the sound quality. By controlling these bands, we can improve the clarity and overall listening experience. For this project, we selected the FIR filters for the equalizer design. One main reason is that the FIR filters are always stable and they provide a linear phase response. This means the original waveform shape of the audio is preserved, and which is very important for sound quality. If phase distortion occurs, the audio can sound like unnatural. We also apply a Hamming window to reduce the unwanted ripples in the frequency response. The equalizer is designed as a three-band system to cover the main audible frequency range. The baseband covers low frequency from 0 to 200 Hz, which mainly affects the bass and low tones. The mid-band from the 200 to 2000 Hz contains vocals and most of the instruments. The frequency above the 2000 and above are classified as treble, which add brightness and detail. Each band use a different FIR filter type to isolate the desired frequency range. In MATLAB, we first define the cutoff frequency of bass and treble at 200 and 2000 Hz. A 400 order of FIR filter is used to obtain a clear separation between the frequency bands. Before designing the filters, the cutoff frequency are normalized with respect to the decreased frequency. Then three FIR filters are created: a low pass filter for bass, a band pass filter for mid range, and a high pass filter for treble. A Hamming window is applied to ensure a smooth and stable frequency response. This slide shows the real-time equalizer interface developed in the MATLAB. The interface includes three gain sliders that allow the user to adjust bass, mid, and treble with a range of plus minus 12 decibel. There are also play and stop buttons that allow a real-time listening where any slider movement immediately affects the audio output. In addition, the user can generate the proof graphs such as the waveform, the spectrum, the spectrogram, and the filter responses. This processed audio can also be exported as a WAV file using the current slider setting.
This slide shows the equalizer sliders interface with bass boosted to 5.9 decibel, mid slightly reduced by -3 decibel, and treble boosted to 6.9 decibel. This setting enhances bass and clarity while slightly reducing mid-range dominance. This slide shows the time domain comparison between the original and equalized audio signal. The overall waveform shape remains similar, indicating that the equalization does not distort the signal structure, while the equalized waveform has a slightly higher amplitude due to its boosted bass and also the treble bands. Normalization is also applied to ensure there is no clipping after amplification. This slide presents the frequency domain comparison between the original and also the equalized signals. So after equalization, the bass and treble region show higher magnitude, while the mid-frequency region is slightly attenuated, which directly reflects the selected slider settings. This confirms that the equalizer effectively modified the frequency content as intended. Next, for this slide, shows the overall equalizer frequency response obtained by combining all the three filter bands. The plot indicates the boosted bass and treble frequency with a reduced mid band, confirming that the equalizer is operating according to the selected settings. In summary, a FIR filter bank's audio equalizer was successfully implemented with independent control over bass, mid, and also treble bands. The system allows real-time adjustment while maintaining a stable performance. and its effectiveness is validated through time domain, frequency domain, and also time frequency analyzers. And that's all from us. Thank you.